A cross B dot C. Later in our study of physics, we will encounter quantities represented by parentheses A vector A cross with vector B dot product with vector C. Prove that for any three vectors A, B, and C, A dot B cross C is A cross B dot C. Calculate A cross B dot C for vector A with magnitude 5, angle 26 degrees measured from the x-axis toward the positive y-axis, positive x-axis to y-axis, vector B with magnitude 4, angle 63 degrees, and vector C with magnitude 6 and in the positive z direction. Vectors A and B are in the xy plane. Okay, to show that A dot B cross C is A cross B dot C, first I have to look at what is B cross C. So B cross C, if you remember, can be found by calculating this determinant I hat, J hat, K hat, Bx, By, Bz in the second row, and Cx, Cy, Cz in the third row. So this gives us, if we evaluate this with respect to the first row, so plus minus plus, for plus I hat we have Bycz minus Cybz. So we would be crossing the first row and the first column, and then we would be multiplying By with Cz and Cy with Bz and subtract these. So we would obtain for this calculation Bycz minus Cybz I hat. And for the second row, for j hat component, we would cross out the first row and the second column, and that would give us Bxcz minus Cxbz. Okay, so for the second term, we have plus Bxcz minus Cxbz with minus j hat will become Cxbz minus Czbx j hat. I have already operated the minus sign. And for the k hat component, we cross the first row, the third column, so we obtain Bxcy minus Cxby. Okay, so this is what we are doing, and we obtain plus Bxcy minus Cxby in k hat. Okay, so if I take the dot product, so I do the dot product A dot product B cross C, then I would have the AX and B cross C's X component, which would give me AX BY CZ, and then I will have minus AX CY BZ, and for the y component I will have AX AY CX BZ minus AY CZ BX, and for the z component I will have AZ BX CY minus AZ CX BY. Okay, so we're going to repeat this exercise for A cross B dot C now. So I look at A cross B. A cross B will be evaluated by looking at this determinant I hat, J hat, K hat plus minus plus AX, AY, AZ, BX, BY, BZ. Now we can do this quickly. This is going to be AYBZ minus BYAZ in I hat. And then we will have AXBZ minus BXAZ what multiplied with minus J hat. So we have BXAZ minus AXBZ J hat. And for the K hat, AXBY minus BXAY. AXBY minus AY BX in K hat. So when I calculate A cross B dot product with C. So for the X component, I have AY BZ CX minus BY AZ CX. For the Y component, I have BX AZ CY minus AX BZ CY. And for the Z component, I have AX BY CZ minus AY BX CZ. Okay, so I'm going to compare this with the previous one. So let's look for AYBZCX. Do I have this term? AYBZCX. So that's this term here. So that term is present. Now I have a term minus BYAZCX. Minus BYAZCX. Do I have this term? Minus BYAZCX. I have this term right here. And let's look for BXAZCY. BXAZCY. BXAZCY is right here. Okay. And then I have minus AXBZCY. Do I have minus AXBZCY? It's right here. And then I have AXBYCZ. Do I have AXBYCZ? Yes, it's right here. And do I have minus AYBXCZ? Minus AYBXCZ is here, and that's basically that's including all the terms here. So my conclusion is that all terms equal. So by comparing the A cross B, A dot B cross C with A cross B dot C, I can see that they are the same thing. Now, is there an easier way to do this? Well, there's an advanced, more advanced topic that's using Einstein summation notation. This proof is actually easily done. So just to give you some extra information here, we have A dot product with B cross C can be written as sum over the component ith component of A vector, ith component of B cross C vector. In Einstein summation rotation, this is written in short as AI B cross C ith component. That basically implies there is a summation when there's a product of two components, two equal components. So B cross C, ith component, can be written as epsilon sub ijk, bj, b sub j, c sub k. So this is basically another way to write this determinant, where this epsilon ijk is equal to epsilon jki is equal to epsilon kij, which is plus 1. And on the other hand, if you do epsilon jik, this is epsilon ikj, epsilon jki, it's equal to minus 1. So what we're doing here is go from I to j to k. If you go from I to j to k, it's plus 1. If you go from j to k to I, it's plus 1. If you go from k to I to j, it's plus 1. So this is positive direction. So that means we're doing this in the clockwise direction. We have positive plus 1. If we go in the opposite direction, if we go from j to I, if we go from I to k, jik, or if you go from I to k, k to j, if you go from j to k, so the last one is not right. So this is epsilon kji, k to j to I, kji. This is negative. So that is counterclockwise direction. So these I, k, and j represent x, y, z components. Okay? So they basically I can be x, y, or z, k can be x, y, or z, j can be x, y, or z. So they represent the components. This epsilon ijk is called Levi-Civita or Levi-Civita symbol. Okay, using this symbol, we can write this determinant. Instead of evaluating this determinant, we can write the ith component of the cross product as epsilon ijk bj ck. So that gives us a nice way of writing a dot b cross c. A dot b cross c is a ith component, and ith component of b cross c, which is epsilon ijk bj ck. So this is epsilon ijk ai bj ck. On the other hand, if I write a cross b dot product with c, this is epsilon ijk aj bk, that's the ith component of a cross b, multiplied with ith component of c, summation, but we don't have the summation sign. And this is equal to epsilon ijk aj bk ci. So epsilon ijk is equal to epsilon jki. So this is epsilon jki aj bk ci. Now I'm going to rename j as I, k as j, and I as k. So if you do that, j becomes I, k becomes j, I becomes k. Epsilon ijk, I have aj becomes ai, bk becomes bj, ci becomes ck. So you can see that these two epsilon ijk ai bj ck, epsilon ijk ai bj ck, they are the same thing. So this is another way of showing a rather more advanced technique using the Levi-Civita or Levi-Civita symbol for this calculation. Now, let's look at part B of this problem after this alternative solution. We have vector A magnitude 5 making an angle 26 degrees with positive x-axis, vector B magnitude 4 making an angle 63 degrees with the positive x-axis. So that's this red angle here. You can see 63 degrees, 26 degrees with positive x-axis for vector A. There is angle theta in between A and B, and vector C is pointing in k-hat direction. So if I write this vector in terms of the components, decomposed into its components, vector A is 5.00 cosine 26 I hat plus 5.00 sine 26 j hat. Remember, vector A is in the xy plane. Vector B is its magnitude 4 cosine 63 I hat plus 4 sine 63 j hat, and vector C had a magnitude of 6 and pointing in the positive z direction, so vector C is 6k hat. Okay, so what is the angle between A and B? It is 63 minus 26, which is 37 degrees. So what is the magnitude of A cross B? Magnitude of A cross B is 5 times 4 times sine of the angle between them, 37 degrees, which is 12.04. And A cross B, if you use the right-hand rule, basically you go from A in the counterclockwise direction towards B with your right hand, and your thumb points in the k-hat direction. So A cross B in k-hat direction, which is found by right-hand rule. Right-hand rule. Okay. So what is A cross B dot product with C? That is magnitude of A cross B, magnitude of vector C, and cosine of the angle between them, cosine 0, because A cross B is in k-hat direction, 12.04 times 6, which gives us 72.2 as our final answer. Okay, so to summarize, first we have shown that A dot B cross C is A cross B dot C. We have done it two ways, by calculating B cross C explicitly and A cross B explicitly using this determinant I hat, J hat, K hat. The second row is the first vector, the third row is the second vector components. And evaluating this determinant and taking the dot product and noting that dot product of vector A with B cross C is its x component multiplied with x component of B cross C plus its y component multiplied with y component of B cross C, and finally z component of A multiplied with z component of vector B cross C. We have done the same thing here and compared the terms we obtained from A cross P dot C with A dot B cross C. We found that they are the same, so all terms are equal, therefore these two are equal. And then I've talked about a more advanced solution using Einstein summation notation. This is something you will encounter when you take mathematical physics. So instead of writing this dot product A dot B cross C as sum over I AI B cross C I, which is the ith component, where I goes from X to Y to Z, this can be written in short as AI B cross C I, And we find the ith component of a cross product using the Levi-Civita symbol epsilon ijk bj ck, where epsilon ijk equals epsilon jki equals epsilon kij. For cyclic permutations, it's +1, epsilon jik, epsilon ikj, epsilon kji is -1. These ik and j represent xyz components. So using the epsilon, we have A dot B cross C is AI epsilon I J K B J C K, and A cross B dot C epsilon I J K A J B K C I. I realized that if I rename in A cross B dot C J as I, K as J, I as K, I obtain the identical result. And finally, in part B, we had two vectors on the xy plane, vector A with magnitude 5, vector B with magnitude 4. We decomposed into their components, and vector C is 6 in k-hat direction. We find using right-hand rule A cross B is in k-hat direction, so A cross B dot C is magnitude of A cross B times magnitude of vector C times cosine 0, because they are parallel. So we find that A cross B has a magnitude 5 times 4 times sine of the angle between them, which is sine of 37, 12.04. So 12.04 multiplied by 6 gives us 72.2 for as our final.